let's wait another minute. You know, since we have finite time for the lecture, since the taping happens from A to B, it's helpful if everybody comes on time. Otherwise, people will be listening to blank tape for 5 minutes, wondering what's going on, you know. All right. We're considering, you know, the limited number of lectures and the huge number of topics, right? Obviously, as I told you, I'm going to use the homeworks to guide me on what needs to be done. And there is really, I don't have a fixed number of topics in my mind. We do what we can, and hopefully you don't get disappointed because you didn't hear your favorite things. So I wanted to discuss a little bit about model selection today because that's part of homework 2 that is due exactly in 1 week from today. Not 2 weeks, 1 week, okay, next Wednesday. And the good way to do this is through a real example such as linear regression. So I'm bringing regression problems in the picture, and it's a topic that basically you can take a whole course, and I'm going to spend at least 1 or 2 more lectures. But today I'm going to give you an overview of the topic. And if you already are familiar with the things we covered earlier, things are not very difficult, actually. It's sort of just another Bayesian example. Okay, so we will start in an elementary way, and then we will rapidly progress to various different things. So somewhere in maybe the first few lectures, we discuss about maximum likelihood estimation being sort of equivalent, or it gives you the same outcomes as least squares, and then map estimation gives you the same thing as regularized least squares. Okay, so in essence, I want to revisit those things in the context of regression. So I'm going to start with least squares in the standard undergraduate problem of polynomial curve fitting. Okay. So what's the problem? The problem is we have, this is a supervised problem. We have data x and y. The y here is denoted t, okay? No particular reason, so it's x and y. And the data are noisy. These circles, the blue circles you see, are the data given in this problem. And we would like basically to fit a polynomial of the form that you see here to the data. Now, the idea of regression, right, is not to interpolate these dots, this data, and fit something that has minimal interpolation error. That's not what we're interested, okay? What we're interested is if we fit it in some way, we want to be sure that predictions for any arbitrary x are reasonable. Okay, so we're more interested in predictions rather than how well we fit the given data. And actually, that's the different thinking that you have from the traditional way of the non-Bayesian way, right? I mean, still a lot of people in applied mathematics work with interpolation methods. In a Bayesian reasoning, interpolation is not good for you. I mean, I'm saying this and I'm taped now, but indeed, we don't really care about interpolation, okay? So this term is called here the bias, and obviously it's like having basis functions that they are x squared, and m is defines the complexity of the model, is the the order of the polynomial that we're using. So least squares, basically it says find w so that you minimize this loss function. So I'm introducing here terminology from lectures I have not been able to cover yet, but this, we call it a loss function. And it is basically minimizing the error that is defined by these vertical lines, which involve the given data and the predictions you have for each x with this function that you try to fit your data. Okay, so if you plug in the previous expression, right? If you write this in a vector form and you plug it in and you do your minimization with respect to w, you basically get a system of equations, say w equal to t. T are your given y's basically at the given x's, and this matrix A is basically involves terms that have to do with your monomials x to different powers I and j. Okay, so and the summation here on j is over the number of terms that you have in the expansion, and n is the number of data points. Nothing fancy, okay? Simple least squares. All right. So if you try to fit this to polynomials of order 0, so basically the constant line, you get something like this. All right. So obviously this is not acceptable. You underfit. If you put a linear line, you basically, this is what you get with least squares. Not good. And again, not good in the sense that if you want to do predictions, all right, you're going to be in trouble. But even in this case, you're far away from the data that you started with, right? So not only your predictions are bad, but also your training error is not good. If you go to third order monomials, basically you start doing a little bit better. But the way this line is the actual function that generated the data without noise, and in this case, sine 2 pi x, all right? The data are not on this curve because they are noisy data, okay? And the noise level is not known a priori, right? So we fit m equal to 3 with least squares. This is what you get, looks better, okay? And if you fit with something of the order 9, you do 0 error in your training data set. So basically this curve passes through every training point, but obviously you overfit, and if you try to do predictions, they're going to be very lousy. Okay? So the message basically that you are getting is this traditional least squares, you have to control the complexity of the model, because the more complex the model, the worse basically the solution that you get. Now, obviously, this since least squares we already have seen, and we will see it again today, it is the same as maximum likelihood estimation. You immediately see that maximum likelihood estimation is not good for you. Okay? Here is a plot that I want you sort of to pay significant attention, because it comes in everywhere in different type of applications in machine learning. So first, let me just give 2 definitions here. You notice it says training and test errors. So training is how much error do you do in the data that you started with. So when you try to go back and see how well you fit the given data, that's the calculation, what we call the training error. And test is how well you do at new x points. Okay? The 2 things are separate, so you cannot really evaluate the performance of the model by looking how well you fit in the data. You have to look at another data set. This is what people in other communities call an inverse crime, for example. That's something you hear in the inverse community. You don't supposed to do that. So let's look. This is the error normalized, okay? So we don't really, it's not important at this point. You will read it in the notes. But let's follow the training error, all right? And the test error for different orders of expansion in those monomials, okay? So m is the highest order of polynomials that we're using. So let's concentrate on the training error. Obviously, it keeps going down. It is flat for a significant change from 3 to 8. Doesn't seem too much is happening. And then it goes basically down to 0. Okay? So obviously, if you are willing to use a very high order polynomial, you can make the training error 0, and this was apparent on this picture, right? The higher you go, the better. But notice what happens as m increases. So the testing error also goes down like this, but at some point, all right, it blows up. So when you overfit, the test error goes up, which means you should not obviously use a polynomial of order 9 here. Maybe anything in between here is good, and because everything in between here is good, maybe m equal 3 would be the best option because you have the less computational cost. All right. So actually, if you look at the coefficients w, and this is very important, when you do least squares, for the case m equal to 9, you will notice that they oscillate plus minus, and these numbers, they are not small because they're multiplied by 10 to the 6th. Okay? So the coefficients w are very high, and that's why we will need to do some regularization to keep these coefficients under control in magnitude. Okay? And we will see this shortly. So, so this is sort of a typical thing you expect with overfitting for this particular data set. And also this may remind you maybe that matrix that you solve AW equal to T, that matrix maybe is not very well posed. Okay? So you don't have too many data, the order of polynomial, the unknowns are too high, and that's why you don't get a stable solution. All right. Now, interestingly, if you increase the number of data points, before I don't remember how many there were, let's say 10 or something. Now we go to 15 data points. We notice when we try to fit a polynomial of order 9, some of the problems we had before have disappeared. Okay? Which is sort of weird because it tells you that least squares, the behavior changes with the number of data points that you have. Even though with least squares you try to effectively identify the complexity of the underlying function from where your data came, and that has nothing to do with how many data points you have. So the underlying function here is a sign, right? But it seems, as I change the data set, the issues that I had before with overfitting is not really there, and I can really push it to m equal 9. So the complexity, the appropriate complexity with these squares changes with the number of data sets. And even, better, you notice if you have 100 data points, yeah, it's, your least squares is doing pretty good. So maybe if you were happy with your least squares, it was only because you had a lot of data sets. Okay, if you don't, then you're in trouble. Okay. Have to keep going and going. So what people do in mathematics, right, is they modify this loss function to incorporate what we already have called regularization. This is not a penalty term, right? I don't have a lot of time to philosophize. It's not that lambda is a huge number. Actually, lambda is a very, very small number. 10 to the minus 7, 10 to the minus 8, The idea here is when you have overfitting, like in the picture I showed you, the coefficients W are very high, plus minus 10 to the 6, right? So this regularization term, it says do the minimization, minimize this error function, this loss function, but keep the W's in magnitude small. Okay? So now there are, so this is, the classical Tikhonov regularization. And we already have discussed other sort of regularizations where instead of W, you have gradients of W, you can have Laplacian, and lots of people who work in imaging, they have their own sort of type of regularization techniques appropriate for each problem. But right now, I am not going to tell you what lambda is. We're going to play with lambda, and I'm going to show you that lambda controls the complexity of the model. Okay, so the results with regularized least squares will be very different from what we saw with plain least squares. So the only difference, when you minimize this, the only difference from before is the addition of this term here in the diagonal of the matrix A that you're forming. So you can think again that A is not well posed, and effectively by adding very small numbers in the diagonal, you make it well posed, so you can address this. This is a well-known trick, right? If you have AX equal to B and you cannot solve it, go and add 10 to the minus 10 in the diagonal, and suddenly things seem to work, okay? But I would recommend when that happens, don't be excited, because, unless you understand the effect of this lambda. So in this case, again, goes in the diagonal. All right, so so here is a case with a polynomial of order m, okay? And the regularization, the lambda, I'm writing here in terms of log of lambda equal to minus 18. So lambda is a very small number, all right? And you notice m equal to 9, no big deal. You get actually a very nice fitting that has a good predictive capability. So the issues that we had before have been eliminated now, because the complexity of the model is not simply defined by m equal 9, but is defined also by that lambda, all right? The regularizer controls how complex the model can be. So in principle, by using the regularization term, it tells you you cannot use complex models, all right? It doesn't allow these W's to oscillate and perfectly fit whatever noise you have in your given data set. Now, if your regularization parameter, it's huge, right? So this is like a minus infinity, so then you're in trouble. And that makes sense, right? Because if you look at the regularization thing, if lambda is huge, it will force all of the W's to be basically 0. All right, so you will basically get only the bias term. Okay, I haven't given you all the details here, but you will get only the bias term, and sort of, you will get a straight line basically. And obviously this is the wrong way of doing this. So you do need regularization, but if you use too much regularization, that's not good for you. All right, so in this case, with regularization, basically you can see that the behavior of the training error, it's a little bit weird, all right? You expect the training error to go down to 0, but the regularizer will not allow that to happen. So you get sort of some plateau, which is very small training error, but the good news is the test error decreases and also reaches a similar plateau. So effectively, this is in terms of the regularization parameter, but notice importantly here, a huge range of lambdas that basically give you the same errors. I mean, if there was one lambda that does the job, I will worry. The idea here is you can go from lambda, let's say 10 to the minus 6 to 10 to the minus 15, and the answers look to be equally good. Okay? And there are lots of techniques in in the literature on how to select lambda, but it's of no interest to this course, right? So we basically wanted to see this in the context of Bayesian things. So let's move to Bayesian then and see how least squares and regularized least squares come to play a role. So the idea is in Bayesian thinking, we are going to introduce some probabilistic models for the parameters W. And in particular, we need to be able to account for regimes where there are no data at all. So in this case, how can you do any predictions here if you don't have any data, right? So you need sort of to have some prior models that tell you what type of functions you expect, in this type of problems. Let me be sure that I am jumping to the correct slides because we're limited time-wise. Okay, so effectively, here's the departure from your classical non-Bayesian, non-statistical methodologies. We're going to make the coefficients W in the, in our model, random variables. And in principle, let me just philosophize on this. I don't want to go, you remember our expression, right? It was W0 plus W1x plus W2x squared, etc. Effectively, if W are random functions, basically the Bayesian thinking says the following, that there is no such a thing as a function that fits the data. There is a distribution over functions. This is very important, okay? And in the Bayesian way, even though you can see we're going to put a probability on this W's and we're going to compute a posterior the way that you see in this equation, at the end of the day, we don't really give a damn about W. Am I allowed to say that on the slide? Yeah, okay. So we don't really care about W, right? As a matter of fact, to do predictions, we're going to get rid of all the W's, which in principle means we're going to average over all possible solutions that our regression model implies. Okay? So, so when you do this sort of analysis, don't go and start plotting W's because nobody cares what W's are. Okay? W's are sort of an intermediate step in going to our objectives of making predictions. So again, we are going to put a prior, there is a likelihood, there is a posterior, and this normalizing factor is what we're interested, hopefully, to explore today in the context of model selection. So let me jump to slide 30. We already have seen this in different contexts. So here is how the probabilistic model for the Bayesian model for regression is going to work. Okay, so we have these data points, these blue dots, that they are noisy. So we're going to fit a distribution over functions, and the distribution over functions is going to have a mean function that is the way that you see here, and that mean function will look similar to the mean function we used to start with today. Okay, that polynomial expansion we had, that will be the mean function. So for every x, in this case x0, all right, we're going to have a distribution of the responses, okay, with a mean that is going to look like the expansion we had before, and then some noise that is defined by the precision beta. And right now, I don't want you to worry what is beta. We will, in doing this problem correctly, we will compute what beta is, but today, let's assume that this noise level is no. Okay, so here is the key equation I want you to remember as we move through the slides. Okay, our regression model is going to give me at every x what the response is, and that will be a distribution. And that distribution, I take it to be Gaussian, that's going to have a mean y of x and w. So you can think of this again. W0 plus W1 times x and W2 times x squared, or some other forms, okay? So whatever we had before is going to be our mean function and then some noise, okay? So this is the Gaussian, and this is basically the mean prediction. And by the way, yeah, it's nice to know the mean prediction, but we will be able to do much more than that because this model, will allow us to compute, the confidence of the predictions. Obviously, we're not going to use this equation for predictions, right? Because these equations involve W, and we don't want W there, right? We will get rid of W. But our model is based basically on this simple way for defining this, the mean function. Okay, so if you, let's rapidly look through the maximum likelihood estimation. And this, by the way, it's identical to what we have done for some other problems, examples earlier in the course. So if you use the likelihood, all right, and you take the log likelihood like that, can you immediately recognize that maximizing the likelihood is the same as minimizing this error function? So it's least squares, if beta is known. Okay, so it's your classical least squares problem. Okay, so so likelihood MLE estimation is identical to least squares, so you will have exactly the same problems as least squares, so it's not good for you. Now, in addition, by the way, to this minimizing this function, you can compute an MLE estimate of the noise beta, I told you we will assume it to be known, but if you already have your data sets and you want to fit some reasonable value on beta, there is a point estimate if you take the derivative, so this with respect to beta and set them equal to 0. Okay? Now, if you are non-Bayesian, it's good that I noticed this word there because I forgot to mention this before, right? If you don't really want to be Bayesian, here is a way that, so if you, let's say, you do your least squares, you minimize this, you find an MLE estimate for W, you find an MLE estimate for beta. If you want to do predictions for any x, you can actually use our regression equation the way we started a slide ago and plug in basically W and beta to take the MLE values. This approximation is called the plug-in approximation. You put point estimates of W and beta and you hope they will work. When you do that, that's not Bayesian. Okay? But still, lots of machine learning books, including, Murphy, Kevin Murphy's book, in many occasions, they do these point estimates simply because if you have a lot of data, with a lot of data, everything works. All right, lots of things work. Okay? So, but these plug-in approximations are not Bayesian. Okay? Not Bayesian. So, let's become Bayesian. So we need a prior on W, and we put a Gaussian that has a mean 0 and some precision alpha. And again, I am not going to bother you in this lecture what alpha is. Take some value that you like, and so it's fixed. So we are going to compute a posterior for W. This bold X is my data, and these are the corresponding Y values at the data points. Right, so when you see X, bold, and T bold is my data. So the posterior of W would be the likelihood, which we wrote it before, times the prior. Now, I am going to write this, I'm going to calculate the maximum of this posterior. So I want you to remember, this is a Gaussian that involves the term W transpose W, and I also remind you that the likelihood had this error term here, all right? So obviously, when you take the log posterior, will you agree with me that involves basically minimizing this term? Right? This comes from the prior, this comes from the likelihood, and do you agree that this is regularized least squares? It's identical to regularized least squares. The only difference, and I think this is wonderful, is you don't really have any more to use some weird methodologies for computing the regularization parameter. The regularization parameter comes directly to be the precision of the prior divided by the precision in the data. Okay? So there is sort of physical meaning, and it comes naturally as part of the Bayesian analysis. So this is regularized least squares, and we don't want that, right? We want to do better. We want to do full Bayesian analysis. So actually, this slide is all that you need to know on how you're going to do Bayesian analysis, right? So this is our prior, all right? And this is the likelihood. And rather than using x and x squared and x cubed, right, I plug in there, x and x squared and x cubed are functions of x. So my regression function was phi transpose, which is the vector of my, let's say, polynomials that I had before, or any sort of functions that you used. So my regression function is phi transpose times W, so I write this in a vector form. Okay? Really, so in our trivial example, it was phi of xn was 1 for the bias term, the constant term x squared, etc. Okay? So this is the likelihood, this is the prior. So okay, so I'm expanding here the likelihood, all right, and I'm keeping only the terms that involve W. So the posterior will be the product of this and the product of the likelihood, and it looks like this. There's no algebra involved, you just substitute it, So when you look at the equations, don't say I'm getting a headache, because there's no headache. You just multiply this by that, and you do that. If you hesitate to do algebra, statistics, and many other subjects in mathematics, right, they are not an ideal subject, you know. So algebra here doesn't scare anybody, okay? So W transpose W, there's a W transpose W, and there is only one term that involves W transpose. So obviously, when we see W transpose W, that reminds us what distribution? W transpose W, right? It's W squared if it was scalar. So what type of distribution we expect to get from this? Gaussian. And what is the trick that you need to become experts? Completing the square. So if you complete the square, there is the final answer. The covariance comes to be Sn, where the inverse of that is given by alpha times the identity matrix. This contribution here comes from your basis functions. This matrix phi transpose is the matrix is the design matrix basically formed by evaluating the basis functions at the given data set points x subscript n from n1 to n, to capital N, okay? And so this is the covariance, and the mean comes to be this nice expression here. So nice, we got basically, we got, you know, W as a nice Gaussian, all right? But as I mentioned, we don't really care about W. W sort of, it's an intermediate step. That's not the end of the story. It's like, what do I do with W, okay? Well, here's what we do with W. I am going to write a predictive distribution at a new point, little x, that is unbolded there. You can see this x here. That x there has no bold. This is my data set. So the predictive distribution, remind me, is the integral in the parameter space of what? So what do I have there in the predictive distribution? If I want at a new x to find what the response t is, what am I doing here on this integral? What is that? What's the first term? The likelihood, and that's the posterior integrate over the parameter space. Okay? Exactly, I mean, the same way as anywhere else. So now, just to show you that if you basically go back and look at the notes on the calculations we're doing with Gaussians, right, and why these are important. So the posterior is a Gaussian, right? And as a matter of fact, the posterior, okay, it's here, right? So it's a Gaussian, we calculate it, and the likelihood is also Gaussian. So actually you have a distribution that is Gaussian, and the mean is a linear function of W, right? Something times W. And here you have another Gaussian. So this fits in directly on our formulas for linear Gaussian models. You remember that? So basically what we need to do is here, we need to integrate W out. You don't really need to do the calculations from scratch. It's not worth it, because this is a Gaussian, this is a Gaussian, this is linear in W, and here are these wonderful results that we had. You remember those? Right, for linear Gaussian systems? So if you look at them once and you were happy, you just look back and you say, for example, what will be x in our problem? X will be our W, all right? And what will be y given x? Well, will be our t, the predictions of the given x, right? So, and where is the linearity coming here? It's ax. Where is my a? Where is my a? There it is, phi transpose. Okay, and but you will say, but it's not a matrix, it's a vector. Big deal, a vector is a matrix, right? So when you do this, here's what you get. Directly by cutting and pasting from those formulas and adjusting to your current calculations for the posterior and the likelihood, you get that at any new point x, the prediction t is a Gaussian that has this mean function m of x, all right? And it has a variance s square of x. Or this is a 1D problem, it's a scalar regression problem. So you notice both the mean is a function of x, and the variance, the error that you do at each point, is also a function of x. Really, we have we have done 99% of the regression lecture, so we don't even have to come back to it, because effectively the prediction is a Gaussian. The mean has a nice expression here. It looks complicated. Nothing's complicated. And actually, later on, we will philosophize that it's not an accident that here you get sort of this nice expression, phi transpose phi, phi transpose phi. There is a reason why in nature things happen this way, but let's not worry about this now. Okay? All right. So here is your first regression result. Okay? So if you use the data points that we started initially, okay, a few data points, this curve is the sine function that generates the data. This line here is the mean of the predictive distribution, right? There is a mean function. It's a function of x, right? And these are the error bars. This is the uncertainty. This is the error. This is your confidence on the predictions at each point x. So at each point, you say, you know what? If I want to do predictions here where I don't have any data, this is my mean prediction. So at this point, this is what I predict, but plus minus that. Okay? Now, if you want to take samples of the regression functions, you can do those as well, and I'm going to come back to it at another lecture when we revisit. But for now, if we fix these parameters alpha and beta, we can actually do wonderfully by not only having a mean regression function, but also having error bars on the top of it. Least squares, regularized least squares will never give you that. Okay? So there is a reason for being Bayesian, and you see it on this picture. All right. So let me talk a little bit about model selection. So we already discussed that computing, for example, the using maximum likelihood, computing the training error is not really an indicator of how well you do, because in essence, the more complex your model, the smaller will be the training error, but the prediction error basically will keep going up and up, right? So that's not very good. So if you're non-Bayesian, so what do non-Bayesian people do? Okay, so non-Bayesian people use what's called cross-validation. Now, by the way, some Bayesian people use that as well, but keep in mind this is non-Bayesian really. Okay, so non-Bayesian people, what they do is, imagine that you have your data set is all of these points that you see there. Okay, so what they do is, let's say they split the data sets in 4 pieces, and they use 3 of the pieces to train the model, and then the other 4th piece to evaluate its ability to do new predictions. So they calculate the test error using 1/4 basically of the data set that they started with, and then they alternate. They say, in my next run, I'm going to use this to do my testing. This is the training, and then they average. Okay, and in some of these problems, they use them to calibrate whatever parameters they have. So this is the idea of cross-validation. In this case, it's 4-fold cross-validation. Okay, lots of people in machine learning still use it, but it's really not Bayesian, because in a Bayesian setting, you only have one data set, and you want to use that whole data set to complete the whole picture. Okay, you don't want to discard this piece and say, I'm going to use this for training, because how about if your data sets are only 10 points? So what? You will get rid of 2 points and make your life miserable? Basically, you don't want to do that. Okay, but again, if you want to use cross-validation in addition to other things, you can do that. But keep in mind, it's not literally, it's not a Bayesian way of doing things. Okay, I think, if I remember, did I give you homework that is due today, right? Where we discussed, we discussed about this Akaike information criterion as a way to control model complexity. Was this in your homework today?
We had the Bayesian information
the Bayesian, so you are even Bayesian, wow, okay, all right. So this is, not even Bayesian, okay, all right. So you are ahead of me. So effectively, in the pre-Bayesian world, right, rather than using the log likelihood basically to see how well you do, you penalize that by subtracting the order of the polynomial, the model complexity. All right? Because you can see, if you try to maximize this, right, because there's minus mu, this will be required that m is small. So the idea is, even in the non-Bayesian world, they say try to use as low complexity model as possible, okay? But we will try to do a little bit better, because this, this model cannot be derived actually from a Bayesian setting, so is not being used. You should not use it, basically. Okay, so let's see how well we will manage to finish everything today. So, when we did regression, right, we play with one model. So now let's consider many models. So in the context of regression, you can think many models means polynomials for the 2, 3, 4, 5, or can also mean this parameter with this value, that parameter with another value. The idea is here is we have a lot of different models, and I denote these models little m. Right? So these are not parameters, these are models. And in a Bayesian setting, you can do miracles. So this is the posterior over models. All right? So let's, interpret this. Basically, you have different models, and you compute a posterior. And you can imagine that really you want to select the model that maximizes that posterior for the given data set. So how do you calculate this posterior? Bayes' rule is the likelihood. All right? Now you notice there are no parameters there, because the parameters have been, what have we done with the parameters? I don't see any parameters there. We know for regression we need parameters. So where are the parameters? What have we done with the parameters? Integrate them out, okay? And pi of m, right, is a prior of models. And if you don't really know which model is better than another, you can actually use a uniform prior, which somehow in the slides, if you see this being set proportional to that, don't panic, because usually that implies immediately that pi of m is uniform over the models. Now, so it will come up that the best way to evaluate models is what is the normalizing factor in our Bayes rule that we wrote in terms of parameters, right? So for a moment, forget that m is there, right? This refers to a particular model m. Forget that this m is there. Do you agree that this integral of the likelihood times the prior in the parameter space is the marginal likelihood, right? From Bayes' rule. We never use it up to now because you don't really need it for the type of things we have done. But in the context of model comparison and selection, we will need to be able to calculate this marginal likelihood. And we said what happens to the parameters. Well, you can see now the parameters theta have been integrated out in this expansion. So in the previous expression that I had, where was it? So in the previous expression, right? This is what this term we're talking, right? So this is this marginal likelihood. But in essence, this is the posterior if pi of m is a uniform distribution. So this evidence would be significant. All right, so let me, I'm going to try to give you only the essence of what we need to know, okay? So let's look at model MI, capital MI, okay? So one of the models. So this equation is basically Bayes' rule the way that we know. So for a moment, if it looks complicated, there's nothing complicated. You can get rid of MI. MI means this is for model MI. Okay, let's get rid of MI. So the posterior in parameters, for the parameters, is the likelihood, all right, times the prior for model MI divided by the marginal likelihood of the data. Okay, and again, the marginal likelihood is for the given model MI. So how do we compute now a posterior over models? Well, a posterior over models, by using Bayes' rule, it requires that we know the marginal likelihood, and the marginal likelihood is this denominator, and this denominator is the integral of the numerator. Okay? This is the prior of model MI, and what is pi of x? I mean, we said this, this here is the evidence, the marginal likelihood for model MI. So what is pi of x? So what is that pi of x in the denominator there? I don't see an MI there. So what is pi of x? You see in this equation here, I'm doing inference over models. So pi of x, right, doesn't have, any models on it. Why? Because the summation of, it's the normalization factor in the numerator, and to normalize this, you have to sum over what? Over all models. Nice. Okay? So here is basically what we have. The margin of the data, the evidence for model MI is the normalization of this. And if you want to calculate this posterior, in this case, of course, we said you need to know this, but if you really want to only compare two models, which is in your homework 2 set, if you want to compare two models, model M1 and M2, this term will cancel out, and immediately you can see that this ratio of these posteriors, if you like, for two models, is basically the marginal likelihoods for models M1 and M2 times the priors for model M1 and the prior for M2. And I'm writing this marginal likelihoods explicitly because this ratio here with the two integrals is what is called the Bayes factor that involves models 1 and 2. The way that I wrote it here, so I put actually 1 and 2, but so usually when you have B10 means model 1 and model 0. Okay, so this is what is called Bayes factors, and in homework 2, for a particular scenario, you are going to have to numerically calculate this because you cannot calculate the Bayes factors analytically. So obviously these are integrals when I look at them, right? And they are integrals with respect to these priors. So effectively, you can see at the numerator as being the expectation under this prior of this function, and similarly here, so you can use Monte Carlo to do that, okay? And I'm guiding you in the homework on how to do this. You remember the expectation, right, from lecture 1 or 2 can be computed as the sample average of these functions f, where the samples now will be coming from these priors. So I'm giving you some hints for the homework there, okay? All right, so if you want to compare two models, all right, the ratio of the posteriors is this Bayes factors times this ratio of the priors. If it happens that these are 0.5, let's say 0.5, you have two models, so this doesn't play a role, and Bayes factors will be what defines which posterior is higher and which model to select. But if these priors, they are not equal, then effectively they play a significant role in the decision process, and they can even give you the wrong results or any results you may want to. All right, so you can manipulate this ratio to be anything you want to, so you can fit to any decision you want to make and say, not my fault, for these priors, this is what I had to decide. Okay. All right, so I'm having two examples that actually I'm going to omit, okay? that demonstrate the effect of the priors, just substitutions. But I want to go to a very famous plot that you need to understand it, because everybody who gives seminars, even in the context of very different scenarios, uses this picture. So it is very, very important that you get a sense of what this picture means. So we are looking for a given model M, right? And we said that the model evidence is, or the marginal likelihood is what is going to help us to select the proper model. So if I have a model M, right, the model M is going to try to explain different data sets that may come in the picture. So before we had 8 data points, 10 data points, 50 data points. But the bottom line is, if I sum this distribution in data space, overall possible data sets that are coming from the true distribution of the data set, then the sum over data sets has to be equal to 1. So every model is trying to explain different data sets d prime here, all right? And the more data sets it tries to explain, the worse job we will do, because due to this summation here, it will have to assign smaller probability to each data set. Make sense? I mean, if you try to explain everything, every data set that somebody will give you, and you use a given model M, obviously that model we have to say, for this I have very little probability, for this another little probability. Why? Because the sum has to be equal to 1. All right? So here is what you do. If you plot this marginal likelihood versus all possible data sets, a very complex model will spread around over a big range of data sets, but the corresponding probability has to be small. Why? Because when you sum over all of this has to be equal to 1. Now, if it explains only, a very small number of data sets, then it can assign very high probability. So this Occam's razor, philosophical reasons, historical reasons why it's called what it is, but basically it says that the right model for your job is a model of intermediate complexity. So basically, you don't want something that only explains 2 or 3 data sets, or something that explains everything. You want an intermediate model. So you need something of this intermediate complexity that is indicated here as M2. Okay? I am going to give you actually a wonderful homework you're going to have to program, where you are going to put this calculation in practice, and then when you make it to work, you're going to be very happy that actually it works, because the calculations will not be more than maybe 20, 30 lines of programming, but with some sophistication. All right, so we discussed about this. So in the context of regression, this is a model. M1 is, let's say, a straight line, a very simple model that I can explain only a few data sets, an intermediate complexity model, and then we had this high complexity polynomial that overfits. Okay. And I know you're way too busy, so lots of you don't look at these little programs from Murphy's MATLAB toolbox, but some of your homework problems are already solved in Murphy. I just want you not to run Murphy's program and say, here are the answers. I want you to extract an independent program, understand what it is there, correct the mistakes, run it, do everything independently, because we're going to run your programs and we need to be sure that they work. So for this little regression problem, okay, I did not tell you how for our, everything was Gaussian in the model, so you can trust that both the posteriors and in principle the marginal likelihood for each model, you can calculate it analytically, right, because everything is Gaussian. So if you do this, you can actually come up with a plot like the one that you see here, and this plot has this marginal likelihood, or the posterior, over models for a given data set, which has a few points. And this tells you, you know what? If you only have like 4 data points, the best model is the model that's a straight line. So this plots this marginal likelihood for different complexity models, and obviously we said you have to select the one that has the highest marginal likelihood or posterior over models. So in this case, m equal to 1. Now if you do put a few more, or many more data points, it says, you know what? M equal to 2 is good, it's better. Okay? M equal to 2. So basically you have an automatic selection of the right model complexity that explains the data in your particular problem. So this is, again, it's our Gaussian regression problem. Everything looks exactly as before. And as I said, there is an exact expression for this that actually, if I have time, I am going to show them to you, those expressions, because it's good to put your hands on them. And actually, I am practically there to tell you how you compute this for simple problems. Okay? So we need to discuss how we're going to evaluate, for a given model M, how do we calculate basically the normalization factor in Bayes' rule in the space of parameters, right? Because for a given M, this requires that we integrate the likelihood and the prior in the parameter space. So we want to know, how do we actually do this? All right, how do we calculate this marginal likelihood? So I think we use this calculation on something else, all right, but maybe, it went just passing rapidly, and it was not clear. So let me try to understand this derivation, because if you understand it and you trust that makes sense, then you can apply it sort of to many problems, certainly for distributions from the exponential family. So we're working with a particular model M, so I have, M is not shown because, we want to do this in general. We agree that the posterior is the likelihood times the prior divided by this normalization factor, right? So our objective is to compute this, all right? So what I'm going to do is, the posterior, all right, and has some functional form, and then some normalization factor Zn. So, if the posterior is Gaussian, it will have some determinant term there. It will have e to the minus x minus mu variance inverse, times x to the minus mu, all of these things. So we have some unnormalized term divided by the normalization Zn, and I use the subscript n to remind you that this refers to the data points, right? So this is the posterior. So I do the same thing with the prior. The prior, you have some function terms, and then a normalizing constant Z0. And the likelihood, similarly, the likelihood will have, what have I done here? Let's see, the likelihood will have an unnormalized term, all right? And up to now, like when we did MLE or a map, we only used these unnormalized terms. We didn't really care about the coefficients in front because they don't play any role in theta, but here we're interested in P of D, all right? So the likelihood, I also write some unnormalizing term divided by this normalization for the likelihood. Now, will you trust me if I say that over every functional dependence on theta, etc., that this term and this term will disappear together with this term and that term completely? I mean, if you have a function of theta on the left, a function of theta on the right, don't you think that everything except these normalization constants that I kept out, they will disappear? I mean, you can try this in any of your problems. You will see all, have to disappear. Right? So this better be equal to this times that. So it comes out that the marginal likelihood, it is literally the ratio of some normalizing factors, a normalizing factor Zn for the posterior divided by normalizing factor for the prior and a normalizing factor for the likelihood. So if it happens that all of these distributions are sort of manageable, you know them, like exponential family, then all the normalization factors, you have them, so the likelihood that you need is already available, ready to go. Okay, so let's see one example, and hopefully you will trust me that this makes sense, okay? So I'm gonna do this with a likelihood that is a binomial model, and this is our coin problem, all right? So we throw a coin n times, we get n1 heads and 0 tails, and for this mean of the distribution, I'm gonna use a prior that's a beta distribution. So let's substitute. Will you agree with me this is the prior? This is the functions I was referring before, and this is the normalization for the beta distribution. What is this? This is the function I was referring for the likelihood, and what is n combinatorial n1? That's the coefficient, the normalization term that I was referring before. Yes? Because I'm using a binomial model. And nice. You agree with me that when you have theta a minus 1, theta n plus 1, you will basically get from the numerator, the posterior will be a beta distribution with parameters n1 plus alpha and beta plus n0. So what this says is the normalization factor for the posterior. So this theta terms, right, and these things will disappear. So basically you have this is from the normalization of the posterior. This is 1 over the marginal likelihood. This is from the likelihood. This is from the prior. And this is the ratio that we discussed before. So for a beta binomial problem, the marginal likelihood is ready to go if you want to do model selection. Okay, analytically. Obviously, if it's given like this, right? So you will need to be able to work with beta functions. Okay, these are not these are beta functions, right? These are the beta functions. The beta functions are the normalizations. It's basically the integral. If you integrate this in theta, then you get this function beta of a and b. So let me do, because you like complicated problems, right? So let's do a real problem. Very practical actually, because even for regression, because everything is a Gaussian, this is the type of things you will use. Do you remember, and this is in homework 1, but for scalars, scalar variables, if you have a multivariate Gaussian and both the mean and the variance are unknowns, what's the conjugate prior? So if both the mean and the covariance sigma are unknowns, what is the conjugate prior? Huh? Both the mean and sigma is unknown. No, those were the marginals. Normal, inverse, not gamma because multivariate, inverse wizard. Okay? So, but in 1D is a gamma. Okay? And for those who basically, you can look back in the slides because we did it, etc. And the normalization factor for the normal inverse wizard distribution is given by this beautiful expression that involves the determinant of this scale matrix as 0. It involves k0, nu 0, the degrees of freedom, and this multivariate gamma function. So it looks complicated. And by the way, if you don't trust me, go to normal inverse wizard Wikipedia, and it will give you immediately the normalization factor. So here's the problem. If you want to calculate for this multivariate Gaussian the marginal likelihood, how do you calculate the marginal likelihood? It's very simple. It would be the normalization factor from the likelihood, which is a multivariate Gaussian. So those two terms are there. All the other terms will disappear with, with the prior and the posterior. This is the normalization from this equation here for the posterior. This is the normalization for the prior. So the marginal likelihood is given by this beautiful expression here. So if you want to do model selection, you will basically have to use that expression. Okay? So the first time you see this, you say, from where are these things coming, and why is this program only 3 lines doing model selection? Well, because they already know what this marginal likelihood is, and this is what is being used for this particular model. Okay? And can you do this calculation for every problem? Well, maybe if you cannot do it analytically, right, because you don't have exponential family distributions, you can basically find some other type of maybe numerical integration to calculate this type of things. But for lots of extremely useful problems, these expressions are given analytically. Okay, so I have a few minutes, which is good, because I want to, since, you know, in your homework you had the Bayesian information criterion today, all right? So I'm going to give you some information, but you won't be able to modify your homework because that information is not requested in your homework, okay? So bad luck there. So this approximation that I wanted to introduce is called the Laplace approximation, and it's an approximation for the posterior distribution in parameter space. It is extremely widely used in machine learning to make calculations easy, and effectively, you know what it assumes? That if you have a lot of data, your posterior is looks like a Gaussian around the map estimate. That's what it is. Okay, so the Laplace approximation assumes the posterior in theta is very sharp, and you know, and it's around the map estimate, and it's a Gaussian, of course. Okay, so the way to derive it actually is if you do a second order Taylor series expansion of the log posterior. Okay, so if you actually this is what you get, right? So the posterior for this is written for a given model M. So if you don't like, you can get rid of M and MM here, but it's a Gaussian, and the precision matrix is minus the Hessian of the log likelihood. Okay? Well, it is, you know, so this is, well, because this is derivatives with respect to theta, usually we have seen the likelihood as d given theta m, right? But really the likelihood is a function of theta m, so the arguments here, I reversed them when I was writing this equation, but this is the Hessian of the log likelihood, okay? If this equation looks weird, take the logs of this and think of a Taylor series expansion. You're going to get a constant term from here. You're going to get the second order term, which is, you know, this around the map estimate. This obviously will be this derivative. There is no first order term. How come there is no first order term? Huh? Because it's a map estimate, not a maximum likelihood. It's a map estimate, so the derivative of the posterior at the map estimate is 0. So when you do a Taylor series expansion, you get the constant term plus the second term. All right? So the posterior for a given model, all right, if you have data, it is sharp around theta map, and it is a Gaussian. Okay? So I am going to use this to discuss in the next 5 minutes about the different Bayesian criteria that control model complexity, basically, similar to what you did in your homework. So the calculation is actually simple. Do you agree with me that you don't bother about the MM, right? So this is model M, okay? So you get rid of everywhere this model M, okay? So do you agree with me that the marginal likelihood is basically the likelihood times the prior divided by the posterior, right? I mean, I reverse basically Bayes' rule, all right? So I'm going to take logs, because this is what we need for model selection. I'm going to take logs of the marginal likelihood. So this will be I'm only needing this equation here. So this will be the log of the likelihood the log of the prior. And what is that? What are all those, the last three terms? It's actually minus the log of the posterior, but I do what to the posterior? I use the Laplace approximation. Okay? Then I am taking one further step. I'm going to compute this marginal likelihood at the map estimate. So basically, I'm going to compute this at the map estimate. If you compute at the map estimate, this term disappears. All right? So your marginal likelihood for each model is basically the log of your likelihood at the map estimate, the log of your prior plus d over 2. This is the dimensionality of your problem minus log of the precision metrics, basically. Okay? So you want to do model selection in a Bayesian way. This is the approximation that everybody is using. Okay? And of course, this can involve some calculations, so some simplifications may be desirable, all right, and the different simplifications give you different models, including what you did in your homework, which is the Bayesian information criterion that can be obtained from this expansion if you take the data set to go to infinity. So how is that coming if n goes to infinity? So this is, again, the same expansion, the same expression I had for the marginal likelihood. As n goes to infinity, I am claiming here, and actually you can prove this, right? But you can use also common sense that the precision metric says A grows as n times some fixed metric say 0, where n is the data size. Okay? If you don't like these approximations, this reasoning, there's better ways to avoid it, but then you have one page of calculations. So as n grows, A grows as n times some fixed metric, say 0. So when you take log of the precision metrics, is log of n times say 0. So you're going to get n to the power d here, outside the determinant. It's like having n in the diagonal, so you get n to the d. So you get d log of n plus log of a0. So this is, as n goes to infinity, this term dominates. So you have d, the dimensionality of the problem, log of n. And because n is very big here, and because the likelihood increases with n, the prior is really not important anymore. You remember the likelihood, the more data you have, right, the higher the likelihood. So effectively, this is this big calculation that you did in your homework. Hopefully I gave you the correct form. Is that the form I gave you? Yes. All right. So the calculation basically involves the likelihood, log likelihood calculated the map estimate, minus d over 2 log of n. Okay? So there's no effect of the prior, and some people actually, they don't even bother to calculate the map estimate. Sometimes they use the maximum likelihood estimate there. One way or another, this is a good starting point. How is the model complexity comes in the picture? You can see. It says, yes, you want a model that maximizes the likelihood of the data, but also you want a model that penalizes very high complexity models. So you want D to be as small as possible. Okay? There are non-Bayesian versions of this. I think I give you an approximation. I give you these expressions for a regression model, so you guys can, for the previous regression problem, so you can actually do Bayesian model selection for regression. And 444, really, I don't think it makes sense to jump to another model. Does it? I mean, another slide. We talk about Bayes factors. I'm going to leave it with that. Okay? You may say, if I'm Bayesian and I have to compare two models with Bayes factors, like you will do in your homework, what values do I look to say model 1 is better than model 0? And everybody disagrees, right? But this is cut and paste, I think, from Robert's book that basically tells you that this is higher than 100. There's, very, very strong evidence for model M1. If you're below 100, strong evidence for M0, etc. So you may want to consult this when you compare models, okay? But in some sense, if these numbers, if these two models, the two marginal likelihoods are about the same, be concerned with Bayes factors. What I want you to do read the rest of the slides, because I gave you a few examples that demonstrate that when you compare models with uninformative priors, you can get completely garbage. And this, they come with different names, paradox of this and paradox of that, etc. So if you have uninformative priors and you try to make decision what model to use using Bayes factors, you can come up with completely garbage results. And for that reason, statisticians will tell you never use an uninformative prior. Okay? A few dots there unless it works. Okay? Unless it works for your particular problem. Okay? But please look at it, because, some interesting sort of paradoxes you get out of this type of analysis. So there is a homework. Due next Wednesday, I have office hours today, and I remind you projects, okay? I want no later than the end of this month to have an agreeable project for each of you, okay? So